Hello everybody and welcome to my lecture. This is a part of Physics 100 class for international students at IPB University in Indonesia. Today we will do some exercise or recitation for week 8 discussing about the heat and temperature. The first problem is related to the linear expansion. Suppose if we have 200 meter of steel bar at 20 degrees Celsius and this steel bar was cooled down to minus 30 degrees Celsius, find the shrinkage of the bar if the linear expansion coefficient of steel is known, 11 times 10 to the minus 6 Kelvin. So this is the initial condition, the steel bar 200 meter length, 200 meter long with the temperature 20 degrees Celsius. And then when the temperature is cooled down to minus 30 degrees Celsius, this steel bar will get shrunk, and the delta L, the change of the length of this bar, equal to L naught, the initial length, times alpha, coefficient of linear expansion, times the change of temperature. L naught is 200 meter, the coefficient linear of expansion 11 times 10 to the minus 6, and the change of temperature, the final temperature minus initial temperature, minus 30 minus 20, so we get minus 50 degrees Celsius. So at the end you will see that delta L about 11 centimeter. Okay, let's continue with the next problem. This problem, if we have a 100 gram of ice cube with the temperature 0 degrees Celsius and is plunged into a cup of water with the mass of 200 gram and temperature of 50 degrees Celsius, so find the final temperature of the system if the cup is assumed not absorbing any heat. So the interaction just between the warm water and the ice cube. To solve this problem, we have to consider the phase transition. According to the Black's rule, the heat emitted by the warm water has to be equal with the heat absorbed by the ice to transform this ice into water. And if the heat is still enough, if we still have enough energy, that net energy will be used to change the temperature of the melting ice into a particular final temperature. So you draw this line, ice 0 degrees Celsius. If you put some energy on this ice, this will transform into a water. And the water from 50 degrees Celsius, the temperature will decrease to a final temperature. So we write down the Black's rule. The heat emitted by the warm water is mass of the water, specific heat of the water, times the change of temperature of the warm water. 200 mass of the warm water times C of the water, which is 1 calorie per gram, and the change of temperature of the warm water is 50 minus TF. And this heat will be absorbed by the ice and it will be used to melt all this ice into a water with 0 degrees Celsius. M ice times L, the mass of the ice, which is 100 grams, the latent heat of ice, which is 80 calorie per gram. And to melt all this ice into water, we only need 8,000 calorie. Suppose if the warm water become water at 0 degrees Celsius, we will have 200 times 50, 10,000 calorie. So you supply more energy than the energy needed for ice to be completely melt into a water. So we have enough energy to increase the temperature of the ice, the melting ice, until it reach a particular temperature. So we can put here the next term, m ice plus m water. This is the total water, total mass of the water, the warm water plus the melting ice from the water from the melting ice, 100 plus 200 times 1 times the change of temperature, Tf minus 0. And if you put all this number in, so you'll end up with the final temperature of 4 degrees Celsius. Okay. The next problem corresponds to the heat conductivity. Suppose we have a metal P with the temperature of 10 degrees Celsius, and this metal is connected to another metal which is called Q, and it has temperature of 115 degrees Celsius. And the thermal conductivity of P is 2.5 times larger than the thermal conductivity of metal Q. If the area and length of both metal are the same, find the temperature at the junction. So you can draw the situation like this. You can draw the problem like this. So remember that we have the continuity of heat flow. So heat flowing from P to Q has to be equal with the heat flowing from Q to P, or HP equal to HQ. If you put all those numbers in, so we can equate the left side minus Kp times Ap dot times delta Tp divided by Lp has to be equal with the Q side minus KQ AQ delta TQ divided by LQ. And remember that the thermal conductivity of metal P is 2.5 thermal conductivity of metal Q, or Kp equal to 2.5 Kq, and the cross-sectional area of P is the same with the cross-sectional area of Q, and length of the metal P is the same with the length of metal Q. So we can cross them out. AP and LP can be crossed out. Yeah. So we can write the equation like this: 2.5 Kq times the change of temperature at metal Q is, at metal P is Tf minus 10, and the change of temperature at metal Q is 115 minus Tf. So solving this equation, then we end up with this solution. The final temperature is 25.7 degrees Celsius. The next problem, again still related to the thermal conductivity. We have a window with this dimension 2 meter at times 1.5 meter. So you can find the area. Area is 2 times 1.5, which is 3 meters squared. And the difference in temperature between outside and inside the room is 37 minus 27. So delta T is 10 degree. So the thermal conductivity of the window, also known 8 times 10 to the minus 1 watt per meter per Kelvin. So you can calculate the amount of heat conduction rate using the previous equation, K times A times delta T divided by L. You put all those numbers in, so we get this solution. The thermal conductivity, the conduction rate of this window is 4,000 joule per second, or 4,000 watt. Okay, that's our recitation for today. Thank you very much. If you have a question, just ask me through the new LMS. Thank you.